So the enthalpy change of a reaction, so delta H, is the heat evolved or required in order for the reaction to happen. So anytime you see delta H, this is talking essentially about the heat correlated with this specific reaction that you're looking at. Now, what is the difference between internal energy of a system versus the enthalpy change of the system? So enthalpy specifically by itself, not the delta H, is the sum of internal energy, and it also takes into account pressure and volume. But specifically for enthalpy changes, it's at a constant pressure. So we're just looking at delta H. You don't really have to worry too much about that. If you ever take physical chemistry, PChem, then you'll learn more about that. But just to note, delta H and delta E internal energy are usually very similar unless you have very large quantities of gas reacting. So we have two terms to describe reactions and their enthalpy changes. Those terms are exothermic and endothermic. Exothermic process is whenever your delta H value is negative. That means that heat is being released from the system to the surroundings. So here we have, for example, just a stove burner, right? It has essentially you have fire, and that fire is a result of the reaction. So we're giving off heat to the surroundings. An endothermic process is one where your delta H ends up being positive, and that means that heat is being absorbed into the system. So here we have an example of an instant like ice pack. How does this happen? Like how does it all of a sudden turn cold? So in these instant ice packs, you'll typically have ammonium nitrate and you'll have water. And whenever you like crack the ice pack, it causes the ammonium nitrate to react with the water, and then that reaction itself is endothermic. So it starts siphoning heat away from the surroundings. So it goes into the reaction in order for the reaction to happen. And then what you have, since it took all the heat from the surroundings, what you have is a feeling of cold. So heat being absorbed, endo; heat being expelled out of the system, exo. So we have several rules for using delta H, so enthalpy changes. And for these enthalpy changes, we have very specific types of equations called thermochemical equations. In these thermochemical equations, for example, this one, note that you can have fractions as coefficients. And I'll explain more about that later, but if you see like a half in front of one of our reactants or products, that's okay, it's normal. I know that in regular, what we've been doing previously and what we will do after, you don't really see these, but for these specific thermochemical equations, you can have fractions as coefficients. So the first rule is that whatever coefficients you have, these are directly related to the enthalpy. So let's say we have, for example, we have 1 mole of C3H8 reacting to give off 2044 kilojoules. So these are essentially like stoichiometric factors. 5 mole of O2 give off that same amount, and you can say the same thing for any of the reactants or products and their coefficients. If a reaction is reversed, then the sign will also be reversed. So let's say we flip this around where all the products were now the reactants and all the reactants were now the products. We would also be flipping this to get negative 393.5 kilojoules. And then we have two more rules. When a reaction is multiplied by a factor, then the overall enthalpy is also multiplied. So let's say we had this reaction again, and we multiplied the entire thing by 2. So you can see 2, 2, 2 compared to that original 1, 1, 1. We will also multiply this enthalpy, and you will get this. So whatever you do to the reaction, the equation, you have to do to the enthalpy as well. You have to show and pay attention to the physical states, because essentially look at these two examples. We have H2 reacting with half a mole of O2 to give water. Now on this one we have a liquid, and on this one we have gas. And notice that they have different enthalpies changes. So physical states are very important, so pay attention to those and also show them. So we have certain conditions that we call standard conditions, and these are applicable to gases, solids, and solutions. So for gases, we have 1 atmosphere of pressure, just how we studied in the gas chapter where STP is 1 atmosphere. For solids and liquids, we have the most stable form at 1 atm again, and for the temperature it's usually 298 Kelvin. For solutions, we have 1 molar for the concentration. So these are just some states, some parameters that we have set, and we have measured certain values at these temperatures and pressures. And those values include enthalpy changes, standard enthalpy changes, and standard enthalpies of formation. So these are slightly different. So the standard enthalpy change is when all the reactants and products are in their standard states at these pressures and temperatures, and then they react to form whatever they do. The standard enthalpy of formation is whenever you have your reactants, again, at standard state parameters, and then they react to form 1 mole of a pure compound. So that's very important. It's always forming 1 mole of your product. The standard enthalpy of formation for a pure element is going to be 0. So let's say you have H2 as a gas. That is something in its standard state, because remember, those diatomic elements, that's where this comes into play, where you need to know those things. So we also have standard enthalpies of combustion. It's very similar to the previous two we just talked about. Note for these, we have a lot of carbon compounds. And if you notice, this carbon compound only has 1 carbon, compared to this one over here has 8 carbons. And if you look at the values for them, you can see how much they increase as you increase the carbons. And what I mean by increase is you're giving off more heat, right? A negative enthalpy means that you're giving off heat to the environment. So look at the name. I hope that you recognize that this is part of gasoline. So it makes sense that it's giving off so much heat, because that's what helps power engines and other machines and stuff. So carbon compounds have a lot of energy within their bonds, and then when you react them, you can get a lot of heat out of that. So next we're going to learn about Hess's law. Hess's law is essentially a way to calculate an enthalpy change. Now, it's taking advantage of the fact that there already exists a lot of measured enthalpy changes, and we use those in order to determine essentially an unknown. So instead of just sitting there wasting your time, not wasting your time, but spending a lot of time measuring it yourself directly experimentally, you can use things that have already been recorded and tabulated. So the way Hess's law works is that we're going to be applying those rules that we talked about earlier, specifically these 2 rules. So an enthalpy change is proportional to the thermochemical equation, meaning if you multiply or divide an equation by a number, you will do the same thing to the H. So if you double that equation, you are also going to double the enthalpy change. Now, if you flip an equation, you will also flip the sign of your delta H. So keep these rules in mind. So let's look at how 1 mole of carbon dioxide is formed. It's a 2-step process, and these are the individual steps. Next, we're going to look at how it actually all adds up together. So here, when we add them, we have, you're going to put all your reactants, so all of these right here, on the reactant side, and then you're going to put all your products on the product side. Now, when we add them, we see that we end up getting and I'm going to change color so we can cancel these things out. So you can see we get CO gas over here on this side and also on this side. Anything that's the same on both sides, you cancel out. And then anything else you can possibly combine, you try to do. So here we have that 1/2 and this 1/2, so we're going to combine it as 1 right here. So this right here is what we're adding. So we end up getting just 102 mole on the reactant side, and then we bring down this carbon and we bring down our mole of CO2. So remember, we were making 1 mole of CO2, so this reaction makes sense. And then We didn't have to actually manipulate anything for step 1 or 2. All we had to do was add straight down. So what you do to these values is you add them straight down. And what you end up getting for this particular formation of 1 mole of CO2 is negative 394 kilojoules. So now we're going to take advantage of Hess's law and actually apply it to a problem. So here we have chlorine monofluoride reacts with fluorine to form chlorine trifluoride. What is the enthalpy for the reaction, the enthalpy change, and determine if the reaction is endo or exothermic. So we need to set these reactions up in order to give us what we want. What we want is this. So you want these compounds on the reactant side, and you want this compound on the product side. So you need to look for each of these individually and see where they are in the equations you're given and how many you have. That will tell you whether you need to flip, whether you need to multiply by 2, divide by 2, whatever it is. So let's see, we have CLF. Let's look for CLF in one of these 3. And we find it's right here. Now notice it's multiplied by 2. That tells you you need to divide by 2. The second thing you check for is it on the reactants or the product side? In this case, it's on the reactant side and it's on the side that we need. So we don't do anything in terms of flipping. We are only going to multiply by 2. So we're essentially done with what we need to do to the second equation. Now, we're done with that one. Now we're going to look at F2. Where is F2? We have F2 right here. Now notice it is on the product side. That tells you right away you're going to have to flip. And then also notice there's 2 of them. We only have 1 in the final equation that we want to add up. That tells you that you need to divide by 2. So we're also done with this one. And then finally, we need to see where CLF3 is at. And it's actually right here. So first thing, is it on the products or the reactant side? It's on the reactants. We want it on the products, so we're going to flip. And then also check how many you have. We have 1 right here, and we also have 1 right here, so we're essentially done. So now we figured out what we need to do to each equation, and now I'm going to go ahead and write them all out. So I was writing them out, so I was following what I said over here. And for the second one, I had multiply by 2. I was wrong, so I meant to say divide by 2. So just note that, erase that on your notes if you wrote that down. So what I did was I essentially just followed what I told myself to do over here on this side. So this first one, I flipped it. So now you can see that this OF2 is now on the product side, and I divided all the coefficients by 2. And then I just followed what I needed to do. I divided this second one by 2, I didn't flip it, and then the third one, I flipped it. So now what we're going to do is cancel out what we notice is the same on both sides. Also, note that you may have like halves of a mole on different equations, but those add up overall to, for example, 1. And by that, I mean this O2 and this half O2 right here. Both of these halves add up to 1, right, on the reactant side. And then we see on the product side, we have this O2. So essentially, we can cross all of these out, because on the reactant side you have half and a half, that equals 1, and then on the product side you just have 1. So we got rid of that O2, and now we can also see we have a full OF2, so we can say 2 over 2, right? That's the same thing as 1 whole, plus this half right here. That gives us 3 over 2. And notice that we have 3 over 2 right here. So again, we can cancel that one with that one. Then finally what we're left with is half Cl2O right here and half Cl2O right here. And then what you're left with is your actual products. So now I can go ahead and add everything up, and we're still not done, but I'm gonna write it out, and then we will figure out what we need to do to the actual enthalpy values. So I wrote it out to see if we actually match with our starting equation, and it matches exactly, meaning that we made the correct decisions with what to do for each of these individual reactions. So now we're going to follow again what we did to the equations, and we're going to do this to these values. So this value, because we flipped it, it's going to turn 49.4. We're going to divide it by 2 kilojoules. For this one, we will just divide it by 2. And for this one, we will actually have to flip it. So negative 266.7 kilojoules. And then we will add these up. So I'm going to add these up. So once you add these up, you should get negative 139.2 kilojoules. So we figured out what the overall enthalpy change was. Now, is the reaction exo or endo? Because it's negative, it's exothermic. So enthalpy is a state function, meaning we can also just look at the final state of the reaction, for example, and compare it to the initial, and essentially we can calculate enthalpy in this way as well. So we can use this equation to determine enthalpy changes. The enthalpy changes that you will be using will be coming from this table, or I will give them to you in the problem, as you will see on this next slide. So if I asked you to calculate the standard enthalpy change for this reaction, what you would do, as soon as you see standard enthalpy change, that means you go to that table that has all the standard enthalpies of formation, and you would set it up as this equation states. So essentially what this equation means is N is your coefficients. So any coefficients that you have, for example, 1 and 2 right here, times the amount of the enthalpy of formation given on that table. So I'm going to set up all the products first, and then I'll set up the reactants, and then we'll subtract those two. So here I set up every single product and reactant. So here you can see I took this coefficient for HNO3. I set up the standard enthalpy of formation. Notice that it's kilojoules per mole. It's because we are multiplying by those coefficients. So all the moles cancel out. All the moles cancel out. So here, right on the top, is all the products. And then we are subtracting all the reactants down here. And then when you calculate all this out, you should get negative 71.72 kilojoules. And then based on sig figs, I would go ahead, because that one's limiting, I would go ahead and just round it. Negative 71.8. Don't worry too much about sig figs for these problems. I won't be like testing you and trying to be sneaky, and either you know how to calculate this or you don't. That's about it for this chapter. For calorimetry, please check out the video that I uploaded. It's just a supplemental video. It explains it very well. It shows you like 2 different examples for heat transfer.